Hi, in this session we are going to have an in-depth look at the concept of electric field. So you might ask, why do we need this concept in the first place? What is the role played by electric field? Well, the answer to this question is this, that just like mass is that we had seen earlier in the case of gravitation, when we consider two charged particles, let's say we have these charged particles Q1, Q2 here, we know that in order to apply forces on each other, these charged particles do not need to be in direct contact. They can apply forces at a distance. In such cases, it is often easier to visualize in terms of the cause and effect if we have this concept of a field. What is happening here is that we have proposed a two-step mechanism for the application of Coulombs force on charge say Q2 due to Q1 and alternatively on charge Q1 due to Q2. In this two-step mechanism, what happens is that as soon as you place a charge at a particular location, let's say I have placed this charge small q at this particular point, now what will happen is it will modify the space around it. You can see this modification happening. This modified space or the field of influence is called electric field. Now, whenever another charge, we will call it the test charge as we've been calling that, if that test charge is introduced in this modified space, this modified field of influence will exert a force on this test charge. Let's say I'm placing a charge capital Q this time. Then I know that according to Coulomb's law, this capital charge Q will experience a force. So the visualization that we have in our minds is this, that because this charge Q created this electric field around it, this charge capital Q, when it entered this electric field, it experienced a force due to this electric field. So this is all there is to this particular concept of electric field. If we are to define it or rather quantify it, the formula given for electric field intensity, the electric field intensity meaning the strength of this electric field, this formula is given as, let's say there is this charge that I've introduced in this electric field, then let's say F is the force that it is experiencing now, then the electric field strength or the intensity of electric field is given by the formula E equals F upon capital Q. Now when we perform this experiment in reality, or rather this thought experiment also, what we have to assume is that this charge capital Q that has been introduced in this electric field, it is tending to zero, meaning it's a very small charge. What purpose this assumption serves? This assumption makes sure that whenever you introduce this charge, obviously this charge will also affect the source charges. So this effect should be very less. To do that, we will assume that the charge that we have introduced as the test charge, its magnitude is small. Once we ensure that, this particular formula, E equals F upon Q, does the work of quantifying this electric field with the help of this quantity called E. It is known as the intensity of electric field or alternatively electric field strength. The formula is given as such. So this is the general concept about electric field. Let's try to gain some hands-on experience in finding electric field now. Let's start with the very basic first situation in which we want to find out the electric field due to a single point charge. Let's say we have this charge Q just like it is kept here. Now, if you observe that if I introduce this test charge capital Q now, I can find out the expression for force. The expression for force becomes equal to F is K times Q times capital Q upon, let's say the separation is R, then we have an R square. This is the magnitude of the force, and then if you want to find out the direction, you will write an R hat here, where R hat is this vector. Now you just have to substitute this value of F here in this expression for electric field, and when you do that, you get the expression for electric field here, which is capital Q's will get cancelled from the numerator and denominator, and all you're left with is kq upon r square r hat. So let's try to analyze this formula and draw some conclusions out of it. The first conclusion that I can draw is electric field, just like this electrostatic force, is a vector. You can see it has the same direction as that of the electrostatic force when these charges are positive. So I forgot to mention there, one of the other assumptions in addition to this charge capital Q being small is that this capital charge Q should be positive. This is just a matter of assumptions and conventions, and it kind of specifies the direction of electric field uniquely. For example, if I had kept a negative charge here, then the electrostatic force would have been in this direction. However, if we are talking about the electric field intensity, its direction is fixed due to this charge, and it is given as this particular direction. So yeah, it is a fixed direction. Electric field is a vector. Then the other thing that we can notice is, just like the principle of superposition held true in case of the Coulombs force, it will hold true for electric fields also. So I will write principle of superposition holds true. Yes. So with these two conclusions that are basic conclusions, let's try to find out this electric field due to other kind of charge distributions. We've already found out the expression due to a point charge small q. The expression looks something like this. This time we will take a numerical example wherein, let's say we have these 2 points A and B. This is point A, this is point B, such that they are separated by a distance of 10 centimeters. Let's say this particular point has a charge q1 and this point has a charge q2, and now I'll consider this particular point, let's call it P, such that P lies in the perpendicular direction of line joining A and B, and at this point we have to find out the electric field. I'll call this middle of AB as O, then OP, I have its length as 12 centimeter. All this is given to us, and in fact even the charges Q1 and Q2 are given. Q1 is plus 10 microcoulombs and Q2 is minus 10 microcoulombs. I think this specifies the entire situation. What we have here is these two charges kept at points A and B, and we are tasked with finding out the total electric field at point P due to the combination of these charges. Obviously, these two conclusions that we drew by looking at the formula for electric field will be very relevant here. We will treat the electric fields due to individual charges as vectors, and then we will use the principle of superposition to find out the resultant electric field. So let's apply the math here now. If this is the center point and this AO becomes equal to 5 centimeters, same is the case for OB, then this looks like a right angle triangle if we consider AOP, meaning AP should be 13 centimeters. And AP, you can see, is equivalent to R here because it is a separation between the charge and the point at which we have to calculate the electric field. So I'll call this electric field due to charge kept at A as E1. Its direction will be like this. And then you see that the charge kept at B has a negative sign. So earlier the direction should have been like this for the electric field, but because we have a negative sign here, which will come here, you will see that this formula will give the direction of electric field due to Q2 as this direction. We have E1 there and E2 here. Let's say this particular angle is theta. By symmetry, because we are talking about the middle point here, this angle also becomes theta. And then if you apply corresponding angle theorem, then you will get this angle is theta, and same will be the case for this particular angle. So if you look at this diagram, it is very evident that the vertical components of E1 and E2 will cancel out each other whenever we try to find out the resultant, right? Because due to E1 it will be E1 sine theta in the plus y direction, and due to E2 it will be E2 sine theta in the minus y direction. However, if you notice the horizontal or the plus x direction, you notice that the components are adding up. They both are E1 cos theta and it is E2 cos theta. So what I will have is the total electric field due to this arrangement of charges. Let's say it is given as E. Then the expression for E, first of all I'll write the magnitude. I've already established its direction. It will be in the plus x direction, or I could use a I hat to denote the vector sign. So this particular quantity becomes equal to 2E to E1 cos theta. Now here I've assumed that E1 is equal to E2. You will see that it's a perfectly valid conclusion to take, because if you notice that the formula for electric field, it is kq upon r square, you can see that the magnitudes are same here for these charges, and even the separation from these charges and this particular point, it remains same. It is 13 centimeters in both sides. So we can perfectly use this formula without any qualms. Now let's just apply the formula here. Instead of E1, I can write kq upon r square. I'm only dealing with magnitudes right now. So I have 2 times k, and then instead of q1 or q2, both are equal. I'm just dealing with magnitudes. So I will simply write 10 into 10 to the power of minus 6 to ensure that I write the charge in SI units. So this is kq upon r square, and then cos theta. Cos theta is base is 5 and the hypotenuse is 13. So instead of cos theta, I will write 5 upon 13. I only have to substitute the value of k, which is, I already know the value, it's 9 into 10 to the power of 9. And then the units are newtons, Coulomb inverse square, and meter square. But I don't need to concern about the units here. I will directly write the consolidated units. I'll just ensure that I write everything here in SI unit so that the eventual consolidated unit is also the SI unit. So with those assumptions in mind, if I substitute the value, I get 9 into 10 to the power of 9, and then I have a 10 to the power of minus 5 here. And instead of r, I have to write 13 centimeter or 0.13 meters, which will give me 13 square is 169. So 169 into 10 to the power of minus 4. This will be the r square in SI units, right? And then I have the right to write this electric field in SI units. We did not discuss the units of electric field. Now we get the opportunity to do so. The units of force is newtons and the units for charge is coulombs. So here we get the SI units for electric field as newtons per coulomb. I'll write it here also just for the sake of completeness. Now, it's a pretty complicated thing to calculate. We have 2 into 9, which is 18 upon 169, and then we have a lot of powers, and then we also have 5 upon 13. So basically I checked this numerical up from a textbook. I know what the answer will come out to be here. I'll simply write it. It's 4.1 into 10 to the power of 6 newtons per coulomb. You're not allowed to take this shortcut. You have to solve this question yourself. The answer, just check out, it will be 4.1 into 10 to the power of 6 newtons per coulomb. Now we've learned how to calculate the electric field due to a combination of these discrete charges. Let's take our matter forward. Now we will find out the electric field due to a continuous distribution of charges. So you can see here, we have this circular ring and the charge capital Q is distributed continuously over this ring. Let's say the radius of the ring is A, and we have to find out the electric field at point P, which is located at the axis of this ring, meaning OP is perpendicular to OA, or the radius of the ring. Now, the difference between the earlier case when we had taken a combination of discrete charges and this case is that now charge is continuously distributed over this entire ring. So this kind of creates a conceptual difficulty as to how to visualize that individual charge and find out the electric field due to that individual charge, and then after finding out electric field due to multiple or all the individual charges, we apply the principle of superposition to find out the resultant electric field. So what we do in this particular case is, because in a continuous distribution, we cannot find out that discrete or the smallest element due to which we will find out the electric field, we use this concept of a differential element. So dq here is a differential element. It simply means that the magnitude of dq can be as small as possible, as in it really depends upon us as to how small we want to break this entire continuous distribution into. So that's for the reason of this, it is called a differential element. And then differential element is an analog to a discrete charge. Then what we say is that we will find out the electric field due to this particular differential charge dq, and then if we want to find out the total electric field, we will again apply the principle of superposition. This time, instead of using a summation, which is used in case of electric fields due to discrete charges, what we do is we sum individual electric fields. This sum for the case of a continuous distribution, it becomes an integration sign, and instead of individual electric field, I have dE, which is the electric field due to this differential element dq. So that is the transition from a discrete set of charges to a continuous distribution of charges, and all the concepts that are relevant to us about this transition we've discussed. Now let's try to apply this framework and solve this particular question. So here I have this differential charge element dq. Due to this, if I want to find out the electric field at point P, it will be given as dE. I already know the direction, and the magnitude of dE can be written as k times the charge is dq here, so I'll write dq, and then I have to write r square, where r is this particular separation between points A and P. So I'll write AP square. So this is the magnitude of electric field. I'll only deal with magnitudes right now, and then I can say that the direction is along the direction of r. So here we have to notice another thing, and that is the symmetry of this particular ring. You can see that for every differential element that we take here, we can take another differential element diametrically opposite to this one, such that if we join these two lines, you will find that this is the direction of electric field due to this particular differential charge. Now if you notice that because of the symmetry, the angles will be equal, and the vertical components of these two individual electric fields, they'll cancel out each other. You can see you'll have a dE sine theta here in the minus y direction due to charge at A, and let's say if it is B, then a dE sine theta in the plus y direction due to charge at B. All you want to find out is sum of dE cos theta. So if I want to find out the total electric field, I know I've used the laws of vector addition. Vectors having opposite directions are cancelling out, and the effective electric field this time is integration of dE sine theta. If I take magnitudes here, I'll write dE without bar and even without the arrow sign, so it will mean that it's magnitude. So we have to find out this particular quantity for this setup, and it will give us the total electric field. Notice this formula will give us the magnitude. The direction we have been able to establish already, that due to symmetry, all the electric field will be directed in the plus x direction. Now let's just substitute the value of dE here. So I'll write everything in terms of x, which is OP, and A, which is OA, or the radius of the ring. So if I do that, I have k here, then dq remains there. Then AP square is A square plus x square by Pythagoras theorem. So I have a A square plus x square here, and then cos theta I can write in terms of A and R and r I'll write in terms of x and a also. So what I will get is cos theta is x, which is the base, upon hypotenuse, which is under root of a square plus x square. So this gives me x upon under root of a square plus x square. So this finishes the formula, and I can finally write the units, newtons per coulomb. Let's try to find out this expression. So now we have to integrate with respect to dq. You can see that these quantities a and x, they don't change when dq is taken as this element or any other differential element. So because they don't change, we will take them out of the integration sign, and what we will get is the magnitude of E is given as kx upon under root of a square plus x square whole cube. And then I have an integration of dq. Now this is a very simple integration to find out. In the entire ring, if you want to find out the sum of charges on these differential charge elements, we know that the total charge that the ring carries is capital Q. So we have to substitute this quantity as capital Q. And this will give us the expression for the magnitude of electric field. It becomes equal to E equals KQ, and this time I have an X in the numerator. And in the denominator, let's write it in another and simplified way. I can write it as a square plus x square to the power of 3 by 2. The units will be newtons per coulomb. This gives me the magnitude, and the direction is plus x direction. So we've learned how to calculate the electric field due to a continuous charge distribution also. The next concept that we are going to learn now in this particular session is the concept of electric field lines. This is also a very important concept, and if I were to tell you about electric field lines in just one statement, it would be electric field lines give us the direction of electrostatic forces due to any particular charge or charge distribution. Let's try to understand this particular statement in a better way. So what is happening is electric field lines are essentially a graphical way to represent an electric field. Let's say we have this charge Q here, and then if we want to find out the electric field at this particular point P, let's say this point is O, then the electric field is given as KQ upon R square, where R is the separation between O and P, and then we also have the direction given as R hat. Now, writing this thing always, every time we want to solve this question, is cumbersome. So there we use graphs to kind of simplify our expressions and communicate more information in one go. Similarly, electric field lines will do the same purpose. What we say is they are a graphical way to represent this electric field, and electric field lines are drawn in such a way that if you take the tangent to electric field lines at any particular point, then that tangent gives you the direction of electric field or the electrostatic force that a particular positive charge kept there will experience. So this is all there is to the concept of electric field lines. However, there are some very interesting properties about electric field lines that are derived only if we consider this statement that I just spoke of. What are those properties? The first property is the field lines never intersect each other. How can we say that? Field lines never intersect. Well, we've just established that the tangent to the electric field line gives us the direction of electric field at that point, and if there is an intersection, means at that particular point there are two tangents. So can it happen that at a particular point the electric field is given by two directions? Of course not, and hence we will see that whenever we draw these electric field lines, they never intersect each other. So this is one of the key characteristics to note whether the lines that I've drawn represent an electric field or not. Then the next property that they have is electric field lines are crowded in the areas where there is more electric field intensity, and they are rarer in the areas where there is less electric field intensity. So I can write field lines crowded this means E is high, and the reverse also holds true, so I'll write vice versa. So this is another very important property. And then the third property about electric field lines is that whenever we have a positive source charge Q, then the electric field lines are directed in such a way that the direction is away from the charge. And whenever we have a negative source charge minus Q, the direction is such that the electric field lines converge to that particular source charge. Now this particular definition follows directly from the definition of electric fields themselves, because when we were defining electric field, we assumed that it is the force per unit positive test charge, right? So whatever the source charge, let's say we have a positive test charge, then if you have a positive source charge, you will see that the forces are repulsive. So the direction of forces will be away from the source charge, and when we have a negative source charge, then the forces will be attractive because the test charge is positive in both the cases. So to depict these attractive forces, you see that the direction of the field lines is convergent towards the source charge. So positive charge, field lines originate from positive charges. That's a way to write it. Field lines originate, and if we have a negative source charge, then the field lines will terminate at that point. So I'll write vice versa again. So these three are really the most important properties about electric field lines. I know so far what all we've discussed, we've only discussed in words and written in sentences. And electric field lines are a graphical representation of electric field, right? So let's now make that graphical representation come to life. Let's try to draw electric field lines due to different kinds of charge distributions. So first off, just like we calculated electric field in three different ways, first of all we took a point charge, we calculated electric field, then we took a combination of discrete charges, and then we took a continuous charge distribution. Let's follow the same framework to analyze electric field lines. So for a positive point charge, the electric field lines look something like this. They are radial rays that are originating from this particular positive point charge. And the other thing that you will note, let's say this is plus Q, then if you take a particular distance, then if you go to this point or this point, whatever point, the total density of these lines or the crowdedness of these electric field lines, if we define a radius r and take a sphere around it, it will remain the same. It means that the formula kq by r square, which is supposed to give you the constant value for a fixed value of r, for that the electric field line remains the same. It also means that around the sphere, if you take any point in the sphere, the magnitude of electric field, it will be constant. The other thing to notice, if you take a sphere with a smaller radius, the crowdedness of the electric field lines increase. It can also be understood from the formula for electric field. The formula is kq upon r square, which is inversely proportional to the distance between the source charge and the point at which we have to calculate the field. So as the distance decreases, the electric field lines should become more crowded because they have to depict that the electric strength or the electric field strength has increased, right? So that is why if you take concentric spheres and if you increase the radius of the sphere, the lines will become less and less crowded, and if you decrease the radius, they will become more crowded. And this is how the lines will look like for a positive source charge. For a negative source charge, the lines will look almost like this. The only difference that is created is that this time this arrow is in the opposite direction, meaning that the direction of electric fields is towards the negative charge, or the electric field lines are kind of terminating to the negative charge. So these are for point charges. Now, as we promised, let's look at the combination of discrete charges. Let's say we have two plus charges kept like here. Then, had there been only one charge, then electric field lines would have gone like this due to this charge and even due to this charge. So you might be confused whether there's an intersection here. However, if you notice that what this intersection depicts essentially is this, that there is no field there. These two field lines get cancelled to each other, and the field that will be there would be almost equal to 0. So the kind of field lines, the resultant field lines that you get in this particular direction, they look almost the same as that of point charge. However, in the direction facing to each other, they look something like this. So this is how the electric field lines due to a combination of two positive charges will look like. The other thing to draw here is this arrow, which means that these lines are originating from the positive charges. Let's take a plus and minus charge now. I'll draw it here this time. I have this plus charge and this minus charge. So the field lines will originate from plus charge and go to minus charge. We can draw something like this, and they will be present in these directions also, because field line due to this is in this direction and due to minus is also in the same direction. And this side it will look like this, and here it will come to the spherical charge. So I only have to draw the arrows here. This will be plus, this will be minus. So whenever you draw a field line, draw two things, the lines themselves and also the arrow. Arrow is very important to depict the direction of the field line.